We've been through the 10 steps of optimization and we've seen how that works. However, there are 3 potential complications which can come up: decimals, dotted lines, and ties. So we'll go through each one of those and see the impact it can have on the process of optimization. In optimization, the vertices always need to be whole numbers and not decimals. This is because we're talking about things that can only be produced or sold in whole units. You can't have half a bear, you can't produce half a car, you can't sell half a car. So in the case of the school holding a car wash, they were charging $5 for a car and $8 for a truck. It doesn't make sense to think about washing half a car, and you can't get paid for only washing half a car. So when we solve the vertices, we always need to find a whole number, not a decimal. Sometimes we get a decimal. Think back to the example of John and his stuffed animals, and we'll look at that in just a second. When this happens, we need to find a point near the vertex where x and y are both whole numbers, either in the shaded area or on a solid line, and use that point instead of the decimals. So here was the problem, just as a refresher. John loved his stuffed animals. Man, he's big into his stuffed animals. And we went through that whole process, and as a refresher, here's the graph that we came up with that shows the polygon of constraints here in the pink shaded area. And here are the vertices, and you noticed vertex D was 2.5, 7.5. But what we said is we can't have decimals. So that's an exception now that we're introducing in this new part of the process. You're not allowed to have decimals. So what do you do in that case if you did the calculations, because all of this was done correctly, but we've come up with a decimal as part of our answer? Well, the answer to that is we need to figure out what's the closest valid point that is in whole numbers. If you look at the graph, you can see that point D here is at 2.5 and 7.5. So that's what we found when we did the calculations. But we've just said that we can't have decimals. So let's go back and take a look at the constraints that gave us that graph. And specifically, let's take a look at the 2 equations that are giving us that point. So it's the green line here and the red line here, which is y greater than or equal to x plus 5 and y greater than or equal to negative x plus 10. Because both of those equations have an equal sign as part of their inequality statement, we know that the line that's in the graph are solid lines, and that means that any point that is on that line is part of the solution. So in this case, we want to move to a point that is as close as possible to this point, but is a whole number without any decimal. So if we look at this, we can move up to this point here, and we can see that point 3, 8 is on the green line and still included within the pink space. So that gives us a valid solution that's as close as possible to vertex D. So we could use that now as our solution, which is what's shown here. Now, if it had turned out that that point wasn't actually on the line, supposing this green line had tipped down just a little bit more so that that point wasn't there, it could still be a valid solution. The solution doesn't have to be on the line. It just has to be coordinates where you have whole numbers that are as close as possible to the original vertex. So if this green line had been down a little bit lower, supposing it went something like this instead, you can see that this point here would still be within the area, and it would be the closest vertex, or the closest set of whole number coordinates that are close to the vertex. Once you've selected the whole numbers to replace your decimals in your vertex calculations, you need to use those whole numbers in your calculation of the total value, or in your maximizing function. So if we look at, this is where we're doing our calculations for maximizing functions. For vertex D, we can see now that we're using 3, 8 instead of 2.5 and 7. So we've substituted those values into our equation, and we get a larger total value in this case. Try the next question on your own, then come back to watch the video segment to check your answer and watch the solution.